Hi, this is my video number 13. Alright, so for this this video I'll begin with definition on the velocity of the particle and acceleration of the particle. Then I'll go to the integration for the vector value function. Yeah, so let's begin with the definition. So if the vector function Rt is a position vector, and differentiable with respect to t, then we have a v dr dt. This we define as velocity of the particle. Yeah, and b a, which is we differentiate respect to t and or differentiate r twice dt. So this we call it as a acceleration of the particle. So this is not difficult to understand. Just consider R as position vector, where we have some particle or object moving from some point to other points, right? Where position vector or position is there. This is our RT. Okay, at any point, so you can have a point here, then RT that. If we point here, then the RT is there. Okay, so with this we can evaluate the acceleration of the particle from that point to the other point, and as well as the acceleration of that particle. Yeah, let me give you a example. So let's consider the position vector RT cos 3ti plus sin 3tj and plus t squared k. Find the velocity and acceleration vector. Find the velocity and acceleration vector. Determine the position of a particle. Determine the position of the particle. On a curve where velocity and acceleration are orthogonal. Velocity and acceleration are orthogonal. Okay, so basically this is an easy problem. So we were given the position vector RT, then we want to find the velocity of that, which is dr dt. We just differentiate the given position vector. So we have so this is negative 3 sin 3t, and this we have 3 cos 3t, and that we have to to t. And also we can find acceleration v, which is dv dt. This is, we differentiate those, we got minus 9 cos 3t, you got that minus 9 sine 3t and 2. Okay, for the second part of the question, we determine the position, means we want to find r, where the velocity and acceleration orthogonal. Yeah, so which means when v orthogonal to a, so which means we have v dot a that equal to 0. Okay, therefore from there we can find what t is. You can find what t is. You just dot product with that, so we have 27 sine 3t cos 3t minus 27 sine 3t cos 3t plus 4t that equal to 0. Yeah, so from there we have t is 0. So once we obtain t0, we just substitute into r, so therefore r 0 is, so cos 0 is 1, sine 0 is 0, t squared 0 is 0, so we have just I. So this is the position vector when t is 0. Okay. I have some exercise actually, if you want to do. If a is a differentiable vector function, if a is a differentiable vector function, okay, and has a constant magnitude and has a constant magnitude, prove that a dot dA over dt, this is 0. So how are you going to do this? First, you might want to look at the magnitude of those. So magnitude means we have magnitude of A. So this is a constant. So if I square this, this is the definition of A dot A. So we square the left side, we square the right hand side. So from there you can prove that this statement. Okay, just a through line. So that's a number 1. Number 2, if A is given as 2t squared t and 1, and B given as cos t sin t t cubed, show that d dt A cross B equal to dA dt cross B plus A cross dB dt. Again, it's just very straightforward. Show, yeah, the question here is show that, not to prove that. So which means you perform A cross B and do the dot product, do the differentiation, and this one you differentiate A cross with B, differentiate B cross with A, and then show that left hand side equal to right hand side. And number 3, show that the vector A with component sin t, cos t and sec 2 is orthogonal to its derivative. Yeah, is orthogonal to its derivative at any point. And plot the locus of A. Okay, so show that so what we want to show here, show that A orthogonal to its derivative. So we show that A prime, this is of course function of t. If you look at the function there, a vector function of t, show that this is equal to 0. Okay, you do this. Alright, now let's go to the integral of the vector function. Integral definition: if ft is a differentiable vector function, is a differentiable vector function, and is an antiderivative of R, and is an antiderivative of R t, then you integrate RT dt, this is ft plus c vector. Yeah, so the constant here is a vector, constant vector. Alright, and f is the antiderivative of R. So where c is a vector, constant vector, where c is a constant vector. And for the definite integral, yeah, for the definite integral, if you integrate from a to b r of t dt, this is we integrate. Remember that our r is let me write somewhere here, r as f, t, gt and ht. So if we integrate r, so which means we integrate each of the element. Yeah, so we have integrate a to b ft dt with component I plus integrate a to b gt dt component j plus integrate a to b ht dt component k. So basically, the way we integrate, or all the properties for the real valued function also apply to the vector valued function. So in order for you to integrate this function, you need function to be continuous and so on. Right? If for a piecewise continuous function, you need to split into the continuous parts. So the same thing with the vector function. So again, simple example: if RT given as 2 cos t, sin t, and 2t, then if you integrate of rt, or integrate r of t dt, so which means we integrate each of those elements with respect to t. So we have integrate those, we have 2 sin t negative cos t, and we have t squared plus some constant vector c. So in this case, c you may consider as a c1, c2, c3. And if you want to evaluate the definite integral, say 0 to pi over 2, say for example, of rt dt, whatever you have here, and then we just need to substitute those values 0 to pi over 2, that give us 21 pi squared over 4. Okay, so let's see a bit application, question related to application. Let's say given v as minus t, t cubed plus 4t, and 2t squared. Okay, find the position of the position of the particle at time t. Yeah, given that at t equal to 0, your r is 1, 2, 3. Okay, so the position vector, which means we want to find r. So we know that v is actually dr dt, which is given as those given in the question. Okay, then you want to find r of t, so we just integrate this, integrate v dt. Alright, so what we have, if we integrate minus t cubed plus 4t 2t squared dt. Alright, so what we have, this is a negative t squared over 2, this is a vector, this t4 over 4 plus 2t squared, and this is 2 over 3 t cubed plus some vector c constant. If you use this condition, given t 0, then r is that, then you can find c. Yeah, at t equal to 0, we have r0 is, so what we have, this is 0, 0, and 0, so we have 0, 0, and 0, plus c, this is equal to those things, equal to 1, 2, 3. So which means our vector c is given as 1, 2, 3. So therefore the position vector, therefore rt at any time is given as where is our r? Here, this one is r. So we have minus t squared over 2 plus 1 t4 over 4 plus 2t squared plus 2, and then 2 over 3 t cubed plus 3. Okay, that's the solution. I think this is pretty simple, right? Alright. Now we look at the some of the properties of the integration for the vector function. Look at the theorem. If f and g, if f vector and g are two integrable vector function, two integrable vector function, then we have properties. Number one, we integrate a to b f of t plus g of t dt, which means we integrate this one by one. Yeah, f of t dt plus integrate a to b gt dt. Okay, that's a properties number one. Number two, if we integrate a to b alpha ft dt, this is just alpha a to b ft dt for any scalar alpha. And number three, we have integrate a to b and c, a constant vector. So ft dt, this is just equal to c dot integrate a to b f of t dt, where c is a scalar vector or constant vector. And number four, magnitude of a to b f of t dt, this is less than equal to a to b f of t dt. Okay, so let's prove this. I'm not going to prove all. Number 1, 2, 3 is quite very straightforward. You can do that one. So let me prove the number 4. Yeah, so let C as AB f of t dt, then the magnitude of c squared, so the magnitude of c squared, this is equal to c dot c by definition, and our c is given there, so we just use one of them, is c dot a to b ft dt, and this is just the same as, you can use properties number 3 there, so just the same as a to b c dot ft dt. Okay, so if we take the magnitude both sides, so what we have now is take the magnitude of those, so which means c, we take magnitude of this, this is just the same as magnitude of that squared, right? So we take magnitude the left side, we take magnitude the right hand side, so this is give you magnitude of a to b c dot ft dt. Okay, then this is less than a to b c dot, sorry, there's no dot, ft dt, and then from there you can just rearrange this thing. So this is, we have t squared c, you can take out c, so we have, this is no, equal to c integrate a to b f of t dt. Okay, and then this c, so this is c squared. Okay, you can factor out one of them, you can cancel out one of them, that, so that we have our c is less than integrate a to b ft dt. And if you substitute c, our c is given here, so what we have, therefore we have magnitude of c is integrate a to b ft dt. This is less than integrate a to b ft dt. So that's the proof of the number 4. For others, I think you can do it yourself. It's not that difficult. All right. I don't know. I want to stop here. I want to continue with another parts, because when we do this kind of lecture, we tend a bit faster. Yeah. So I think I better stop here. Then we continue the other part in the next lecture. Okay. So stop here. Bye bye.